right now the biggest and most powerful vehicle that Mazda has ever built.
In the race for auto innovation, there is one innovative maker at the forefront. As other top car makers are rushing to complete electrification, Mazda has been working methodically on a counterintuitive path that might rewrite the car engineering Bible. At its cutting-edge technology research and development facility, engineers have developed an innovation whose potential can redefine the game-altering innovation that can redefine the whole industry. Instead of merely releasing step-by-step advances, this is a pronouncement of technological superiority, a breakthrough capability that will redefine our own assumptions regarding vehicle mobility, performance, and functionality in our increasingly complex world. What then is this hybrid powertrain? Let us discover this innovation. But to understand why Mazda's latest move is sending shockwaves, we need to rewind. Because this isn't just a new engine, it's the climax of a legacy built on defiance, resilience, and bold reinvention. The legacy of innovation. Mazda's CEO has made a sensational announcement that can rewrite the face of the electric car market. The company's breakthrough engine development sent shockwaves throughout the automotive industry, suggesting an epical breakthrough in the imminent future. To appreciate the sheer magnitude of this claim, one must look into Mazda's fascinating past, which has been dotted with phenomenal grit, unconventional creativity, and unwavering commitment to engineering excellence. During the aftermath of World War I, Hiroshima faced severe economic difficulties in 1920. Amidst these financial setbacks, local industrialists established Toyo Cork Kogyo with a vision to revitalize the region with the cork industry. The firm initially focused on producing compressed corkboards that showed a lot of promise until the start of a devastating fire that broke out in 1925 and gutted 70% of their equipment. Whereas this tragedy would have spelt the doom of the fledgling company, it instead initiated a wonderful metamorphosis. Jujiro Matsuda joined Toyo Cork Kogyo as the CEO in 1921 and took with him his engineering degree and vision. Matsuda's vision, Toyo Cork Kogyo, directed the company to diversify, as there was only a limited scope in the cork business. The strategic action by Matsuda toward the manufacture of machine tools not only rescued the company, but also paved the way for later businesses within the automobile industry. By 1931, Toyo Kogyo had diversified into motor vehicle manufacturing with the production of the Mazda Go, a three-wheeled truck that was designed to resemble more a motorcycle with a trailer than a conventional modern vehicle. It was Toyo Kogyo's entry into the transportation market, the spirit of innovation that would make Mazda the company it would later become. The selection of the Mazda name held symbolic meaning. Derived from Ahura Mazda, the Zoroastrian god of harmony and wisdom, along with intelligence, the name symbolized the ideals of the firm to positively help society through wisdom, intelligent design, and harmonious engineering. Additionally, the name had a linkage to Matsuda, the founding family's last name, in that it delivered a personal relationship to the identity of the firm. During the outbreak of World War II, Toyo Kogyo's own contribution to Japan's war efforts was the manufacture of weapons, most notably the Type 99 family of rifles. Although Hiroshima was leveled during the war, its factories were miraculously untouched by the atomic bombing. The post-war era witnessed the difficult task of rebuilding and situating the role of Toyo Kogyo in a world that was perpetually changing. In 1960, the most important milestone was the introduction by Mazda of its first passenger car, the Mazda R360. The compact coupe was intended to address Japan's increasing demand for affordable personal mobility. The R360 was an extremely successful vehicle, offering an affordable and stylish choice for consumers. The success guaranteed Mazda its passenger car future and set the stage for future developments.
Mazda is a small Japanese manufacturer that has gained a reputation for making cars for drivers.
The innovation-oriented commitment of the company was reflected most strongly during the 1960s with their aggressive uptake of the Wankel rotary engine, which was conceived by German engineer Felix Wankel. It was a light, compact engine with a high power-to-weight ratio. The earlier models of the engine were problematic, with durability issues causing the engine to fail after mere hours of operation. This did not deter Mazda engineers from embarking on an ambitious mission to develop and commercialize the rotary engine. Their tenacity paid off with the 1967 launch of the Mazda Cosmo Sport 110, a mass-produced car boasting a twin-rotor rotary power plant. Its success proved Mazda's engineering ability while solidifying their dedication to challenging automobile standards. Mazda's innovative stance extended beyond engineering to encompass design philosophy. Since the company's inception, it has followed its creed of producing vehicles that emphasize functionality and beauty. This dedication can be observed in Mazda's design language, which has sought to articulate the dynamics of motion and refinement consistently. In the latter half of the 20th century, the company had aerodynamic lines and curves in its offerings, finding a balance between form and function. This made Mazda's cars look more beautiful and enhanced their performance. The design philosophy has evolved over time and has now reached its contemporary shape in the Kodo Soul of Motion design theme of today, which embodies the dynamic nature of movement. Mazda's journey has not been without financial difficulties. During the late 20th century, the company faced financial difficulties that threatened its independence. During this period, Mazda formed an alliance with Ford Motor Company, which acquired a significant stake in the Japanese company. The alliance gave Mazda the financial stability it so desperately needed and enabled technology transfer between the companies. Mazda has also maintained its individual identity and engineering culture, continuing to develop its own technologies and maintain a unique brand image. By the early 2000s, Ford had sold some of its stake in Mazda, so that the Japanese company was once again more autonomous and developing independent innovation. Since we are here to discuss the revolutionary engine and why Mazda's CEO believes that it would be the one to conquer the EV market,
EV adoption pace is slow right now. It's faced a reality.
we should first look at where the journey has brought us. But Mazda isn't just about surviving, it's about redefining what's possible. And to understand why its latest engine could shake up the EV world, we need to rewind and trace the path of innovation that brought us here. The evolution of engine technology. The growth of engine technology is a compelling testament to human creativity and the persistent pursuit of efficiency, performance, and environmental sustainability. From the primitive steam engines of the 18th century to the sophisticated internal combustion engines and the development of electric cars, the making of propulsion systems has been the prime driver in shaping the world of new transportation. In the late 18th and early 19th centuries, steam engines became the standard for propelling industrial equipment and trains. The groundbreaking machines worked by a method of heating water to produce steam, which in turn drove pistons or turbines, creating motion. As groundbreaking as they were, steam engines were clumsy, wasteful, and took a long time to get started, making them unsuitable for private use as a means of transportation. The quest for a smaller and more efficient power source gave rise to early gasoline engines. By the mid-19th century, innovators such as Etienne Lenoir and Nicolas Otto had developed internal combustion engines in which fuel was ignited in a closed space in order to produce power immediately. They were lighter, more efficient, and simpler to start than steam engines. The flexibility and versatility of internal combustion engine technology subsequently beat steam power to become the darling of cars when automobiles became ubiquitous in the 20th century. Fuel efficiency and environmental concerns instigated a series of efficiency battles between manufacturers. The 1970s oil crisis highlighted the importance of fuel-efficient vehicles, prompting engineers to seek means to extract more power from less fuel. Meanwhile, growing environmental concerns instigated tough emission controls. Governments worldwide implemented laws to reduce emissions such as carbon monoxide, hydrocarbons, and oxides of nitrogen. The manufacturers responded by developing technologies such as catalytic converters, electronic fuel injection, and variable valve timing to meet these regulations without compromising performance. As already mentioned, In the 1960s, Mazda introduced the rotary engine, which is a light and compact alternative to the traditional piston engines. Unlike conventional engines that made use of reciprocating pistons, the rotary engine employed a revolving triangular rotor within an epitrochoid chamber in order to supply power. Its distinct design enabled it to have a higher power-to-weight ratio and smoother operation. However, the rotary engine faced immense challenges, particularly with regard to fuel efficiency and reliability. Its design resulted in poorer fuel economy and higher emissions, making it less environmentally friendly. Additionally, issues such as apex seal wear led to durability problems. The rotary engine was an internal combustion engine with a different process. These limitations constrained the mass production of the rotary engine, and Mazda eventually phased it out in favor of more conventional technologies. In order to satisfy the twin demands of performance and economy, the latter half of the 20th century and the beginning of the 21st century saw a trend towards engine downsizing. The manufacturers began replacing larger naturally aspirated engines with smaller turbocharged engines. Turbocharging enabled these smaller engines to produce power comparable to their larger counterparts by forcing more air into the combustion chamber, thus enhancing the efficiency of combustion. This technology offered several advantages: improved fuel economy, reduced emissions, and reduced weight. However, it introduced issues such as turbo lag, complexity, and potential reliability issues with increased operating pressures and temperatures. Downsized turbocharged engines diffused broadly in spite of these issues, especially where fuel efficiency and emissions standards were stringent. The late 1990s witnessed a paradigm shift with the introduction of hybrid cars, which merged internal combustion engines with electric drive to achieve maximum fuel efficiency and the least emissions. The Toyota Prius, launched in 1997, was the first mass-produced hybrid car that provided consumers with a product that addressed growing environmental concerns without sacrificing convenience. Then, with the start of the 21st century, electric vehicles picked up traction, spearheaded by the likes of Tesla. Founded in 2003, Tesla aimed to transition the world to clean energy. The arrival of the Tesla Roadster in 2008 and later offerings like the Model S demonstrated that EVs could be high producers, have a long range, and be beautiful to behold. Tesla's success encouraged the traditional automobile makers to invest a fortune in EV technology, marking the likely paradigm shift in the motor industry. Whereas the majority of the manufacturers focused their energy on electric and hybrid technology, Mazda tried to optimize and refine internal combustion engines. This promise was translated into the development of the Skyactive technology portfolio, which was intended to make vehicles more efficient and better performing. Maybe the greatest success of the initiative was the release of the Skyactive X Engine. This game-changing engine combined the best features of gasoline and diesel technologies through the use of spark-controlled compression ignition. In essence, it allowed the engine to burn a lean air-fuel mixture through compression, just like a diesel engine, but with the drivability and more RPM-friendly nature of a gas engine. What was achieved was an engine with better fuel economy, lower emissions, and driving fun. However, even this trailblazing step had its constraints that highlighted the complexities of modern automotive engineering and revealed the challenges of the modern approach to handling industry. The harsh reality of modern cars. Electric vehicles, or EVs as they are commonly referred to, have increasingly become more tolerable and accepted in society, largely due to their greenness. Included among these benefits is the complete elimination of exhaust pipe emissions, which are largely responsible for air pollution, as well as their overall assistance towards reducing our ecological footprint, thereby urging us to live more sustainably. However, we should consider that producing batteries for electric vehicles raises major ethical concerns alongside severe environmental challenges that need to be addressed well. The various extraction processes that are used in acquiring the required battery content materials, which include lithium, cobalt, and nickel, have a tendency to be at the cost of devastating the natural world. All too frequently, These processes are also directly linked to extreme cases of human rights violations occurring in some corner of the globe. Furthermore, it must be understood that the quantities of energy that are associated with the production of batteries will have the impact of negating some amount of the environmental benefits that had been achieved during the operational life of the car itself. Infrastructure constraints greatly hold back the mass adoption of EVs. Insufficient charging points remain a major problem, with adverse effects for the rural and low-income communities. Concerns regarding the power grid's ability to withstand increased usage levels raise legitimate questions on EV technology scalability. Upgrading the grid and expanding the wider charging networks takes huge sums of money and years. Concerns that, by necessity, slow progress toward all-electric transport. Although EVs are typically promoted as maintenance cost-effective substitutes for conventional vehicles, they are not entirely maintenance-free. Their batteries can undergo deterioration over time, which may result in expensive replacement processes, and advanced vehicle parts can require the services of highly skilled experts, which may drive up maintenance charges. Although EVs are more expensive to purchase upfront than most conventional vehicles, hybrid vehicles, conventional engines supplemented by electric powertrain technology are a halfway house between conventional and electric drive technology. But this two-system approach comes with a complete set of problems. The inclusion of both electric motors and traditional combustion engines, together with their necessary control systems, results in a significant increase in production costs. This also results in potential maintenance issues that can arise over time. Although hybrid battery replacement is less common than for fully electric cars, the expense of the batteries is sufficient to put off buyers who are worried about the cost of running the vehicle in the long term. Furthermore, due to stringent regulations governing fuel efficiency and exhaust emissions levels, the majority of car makers have opted to adopt smaller turbocharged power units for their vehicle designs. These units provide an enormous amount of performance relative to their quite unassuming size, although it is noted that they do so under conditions of increased pressure and heat. This particular operating condition might have negative impacts on their overall longevity and durability. Many car owners have reported that they get enhanced wear patterns, which ultimately translate to much higher repair bills over time. This creates a complex trade-off between increased performance and reduced durability, raising fundamental questions and controversies about the long-term sustainability and viability of these types of powertrain configurations. Mazda's strategic decision went counter to the then raging trend that was being followed by most other companies in the auto industry. Rather than embracing hybrid technology wholeheartedly across their entire lineup like many other companies were doing, the company chose to remain steadfast in their belief in the untapped potential of conventional combustion engines. It was this company's conviction that ultimately led to the development of the Skyactive X Engine, a bold and ambitious attempt to rewrite the then-set rules on conventional engine efficiency, as well as the prevailing performance norms in the market. Initially hailed as a truly revolutionary piece of technology, this innovative engine used spark-controlled compression ignition, allowing it to cleverly combine the merits and strong points of both gasoline and diesel technology in a new and innovative way. The system was precisely developed with the specific objective of fuel economy improvement while simultaneously attempting to minimize emissions. Importantly, the design ensured that there would be no trade-off on the potential for performance that drivers and users require. In a real-world application, there was a more nuanced scenario. Despite the engine having improved fuel economy over older models, the project was lagging in the initial development stages. The nature of the system also made it a problem with production and maintenance. The driving performance of the Skyactive X engine was also under criticism. Drivers blamed the sole responsibility on the engine for the need to run at increased RPM ranges in an attempt to achieve optimum power output. This need had a profound impact on driving habits and, in the end, on overall driver satisfaction. In addition to all these direct problems, individuals were expressing their concerns about scalability. The problem of scaling the technology for use in various other car models, while simultaneously meeting a broad range of performance requirements, was proving extremely difficult. Mazda engineers were quite aware that even after the innovation with Skyactive X technology, the engine was not the panacea for altered industry requirements. Staying abreast of technological advancements and evolving customer requirements meant there was a requirement for continuous innovation. It was this realization that made Mazda venture out in pursuit of more extreme solutions in the interest of automotive excellence, which ultimately resulted in work on the new engine that their CEO insists will revolutionize the entire EV market. But wait, that realization comes later. But before Mazda could find its game changer, it had to navigate a minefield of broken promises. Because in the race for the ultimate engine, even the brightest ideas often burn out before ignition. The search for the ultimate solution, the search for the ultimate motor, has encouraged several automakers to go against normal internal combustion doctrine. Over time, revolutionary concepts have emerged that promise to turn the automotive industry on its head. None of them came near to living up to their original potential, however. Each was saddled with some inherent drawbacks, some mechanical, some pragmatic, and some just economic considerations. But each was a step forward toward whatever came next. Hydrogen fuel-burning engines are a great example. The major players, like Toyota and BMW, have invested huge amounts of capital into this technology in hopes of creating an internal combustion engine that uses hydrogen as a gasoline alternative. Theoretically, the concept is ideal. A tried-and-true engine design, an existing manufacturing base, and an exhaust system that emits nothing but water vapor. In principle, hydrogen-powered combustion engines could offer the best of all possible worlds. The efficiency of hydrogen fueling without the need for massive storage batteries. Reality is far from it. One of the most significant challenges is hydrogen storage. To store hydrogen in a usable form, it must be compressed to extremely high pressures, up to 700 bar, that cause manufacturers to install reinforced fuel tanks at additional cost and weight to the vehicle. Second, hydrogen fueling infrastructure is underdeveloped to a serious degree. In contrast to ubiquitous gasoline pumps, hydrogen fueling stations are scarce, and building them is prohibitively expensive. Lastly, there is an efficiency paradox. While hydrogen combustion engines do not produce CO2, they do produce nitrogen oxides, pollutants that cause smog and air quality issues. These concerns have prevented hydrogen combustion engines from becoming the industry standard even after several decades of development. Koenigsegg, a company renowned for engineering groundbreaking innovations, introduced yet another game-changing innovation. Their free-valve technology was meant to revolutionize internal combustion by doing away with one of the most fundamental parts of the engine, the camshaft. Traditional engines incorporate camshafts in order to control the opening and closing of intake and exhaust valves at given instances. Free-valve technology, however, incorporates an electro-hydraulic system that offers separate control over each valve. Theoretically, this allows the engine to optimize its performance in real time, improving fuel efficiency, power, and emissions over conventional setups. The system could even change between different fuel types with minimal adjustment. But complexity is a big drawback. Free-valve technology is expensive to design and manufacture. Although it has been tested in high-performance cars, it has not found favor in mass-market vehicles. The technology requires sophisticated sensors, actuators, and hydraulic components, all of which increase expense and possible maintenance issues. For a business that prizes reliability and price, free-valve technology has not yet broken through, as some had anticipated, at least not yet. Nissan's answer to rethinking the combustion engine was different in the form of their variable compression turbo, or VC Turbo for short. Unlike non-displaceable compression ratio traditional engines, VC Turbo features on-demand adjustable compression. This allows the engine to switch between high compression mode for improved fuel economy and low compression mode for maximum power. The aim was to create an engine that would deliver performance and fuel efficiency without the constraints of conventional turbocharging. The implementation, however, has not been perfect. The VC Turbo's mechanism of physically changing the piston's stroke length adds complexity and moving parts to an already complex system. The additional components add more failure points. There have been durability complaints, particularly about long-term reliability. While Nissan has refined the technology to improve smoothness, the added complexity has limited its scalability beyond niche applications. The engine does function, but it hasn't transformed the industry as Nissan initially envisioned. Meanwhile, Porsche has taken a different approach, one that requires no engine mechanics to be changed, but a change to the fuel itself. Their solution is synthetic fuels, or e-fuels. Unlike regular gasoline derived from crude oil, e-fuels are produced by capturing CO2 directly from the air and combining it with hydrogen to produce a fuel that burns precisely like gasoline but is theoretically carbon neutral. The advantage is obvious. Existing gasoline engines can be powered by this fuel with no adjustment, no new infrastructure, no new engines required, just cleaner fuel. But reality once again has complications. Currently, e-fuels are too expensive to produce. Synthetic energy is high, and without a huge investment in renewable sources, it is hard to ramp up production. Current estimates put e-fuels at about 10 times the price of traditional gasoline, and they are thus uneconomical for mass consumption. Technology is promising, but until production costs are reduced drastically, e-fuels will not replace traditional gasoline anytime soon. Which brings us to the root issue. None of these numerous efforts has discovered the ultimate solution. Hydrogen-burning engines, free-valve technology, VC Turbo, and e-fuels have all pushed the limits. None has brought the ultimate solution. Each has had its own trade-off: cost, complexity, or infrastructure limitations. That is why Mazda was not sure that any of them were the future. For years, Mazda's engineers have been quietly working on something that might be different, something that doesn't just tweak established designs, but redefines what an internal combustion engine can be. What if they'd found a way to merge diesel efficiency, gasoline responsiveness, and hybrid environmental advantage? What if they'd produced something that might challenge electric vehicle dominance not by fighting change, but by driving it? That's exactly what they claim to have done. And now it's time to find out. And now the wait is over. Because Mazda isn't just betting on the future, it's building it. What they've created with Skyactive Z might not just rival EVs, it could replace them. Gen Z. Mazda is now poised at the very threshold of what can only be described as a revolutionary transformation in the automotive industry, as it embarks on an ambitious quest to unveil its innovative and game-changing Skyactive Z engine. This revolutionary power unit is no ordinary development. It is a true quantum leap in engineering advancement, attesting to the company's passion for breaking new ground and redefining performance parameters. The highly anticipated release of this state-of-the-art engine is scheduled for the year 2027, marking a significant milestone in Mazda's technological evolution. As part of a broad and extensive technological overhaul, this novel engine system has been meticulously designed with the specific aim of replacing the existing Skyactiv G and Skyactiv X versions, further attesting to Mazda's passion for innovation in the automotive world. Through a process of precise and detailed design refinement, the Skyactiv Z was developed with great care to achieve a record-breaking level of fuel economy that has never before been reached, while simultaneously being engineered to comply with the most stringent emissions legislation available. These are the stringent Euro 7 emissions standards used in Europe, as well as the LEV4 and Tier 4 standards used in the United States. The Skyactiv Z engine operates frighteningly close to the theoretical combustion perfection point, and it is a giant step forward in internal combustion engine (ICE) technology. According to the company's technical assessment, the ambitious endeavor is a stark and convincing piece of evidence that proves Mazda's unwavering and unrelenting dedication to breaking the boundaries of conventional engine design to unparalleled heights that have never previously been seen in the automotive industry. Even as the auto industry rapidly heads towards the future of electrification, Mazda's top managers have an unwavering and strong conviction regarding the vast potential of internal combustion technology and believe that it remains incredibly valuable. When asked about the possible impact that the new engine could have on the market, Mazda's chief executive officer gave a sensational and powerful response. "Our revolutionary hybrid engine will completely transform the whole electric vehicle industry." The CEO's determination is clear. "These are not predictions. I am making a categorical statement. My mind is absolutely made up. I will follow through on this vision relentlessly until Mazda attains absolute leadership in the modern automotive market. If this requires leading the way with hybrid engine technology, we will set new standards of excellence." The viability of this ambitious strategy is revealed on closer inspection. By concentrating its efforts on producing hybrid technology, Mazda is able to overcome and address many of the largest challenges consumers have against electric vehicles. Those challenges, most notably, are the limitations brought by the relatively lower driving range, as well as the present scarcity of proper charging infrastructure. In addition, Mazda is careful to offer the same quality of driving experience that its customers have become accustomed to and enjoy, without sacrificing the ability to offer vastly improved efficiency rates over traditional cars. The first production use of the Skyactive Z engine technology will be featured seamlessly in the latest model lineup of the CX-5, one of the most consumer-friendly vehicle models. Aside from this, there will also be a high-tech hybrid model that has been developed wholly by the company's own engineers and experts, showing their commitment to innovation. This very precise corporate philosophy falls squarely into Mazda's global corporate vision and philosophies: to create and manufacture cars that not only meet but also exceed the constantly shifting green requirements set by regulators, while maintaining and enhancing the performance characteristics expected and valued by drivers. In addition, the automaker emphasizes that these technologically improved and environmentally friendly cars will actually be made available in the market at prices that are affordable and within reach of a broad segment of consumers. While all others are putting heavy investment into battery electric vehicle development, Mazda's investment into the development of internal combustion technology proves there is an intimate understanding that highly advanced internal combustion engine solutions can peaceably coexist with electrification initiatives, thereby providing customers with diverse options without requiring egregiously expensive investments either in the vehicles or in the maintenance parts thereof. We have now come to the end of our video today. Will you at any point consider buying this new Mazda? Feel free to share with us your thoughts in the comments section below. If you also like this video, make sure to leave a thumbs up, click the subscribe button, and turn on the notifications bell so as to be notified anytime we make a new upload. See you in our next upload.